First, let us take a look at the model that we will use to illustrate the application of Logit Model. In the equation shown here, x is the dependent variable which shows the decision to purchase a car. As we can see, x is a binary or categorical variable where x is equal to 1 if an individual decides to purchase a car. If an individual decides to not purchase a car, x is equal to 0. This decision to purchase a car or not is a function of 3 independent variables. These are income, age, and gender. Gender is a categorical or binary independent variable and is equal to 1 if the individual is a male and 0 if female. We will use a dataset that has 1,000 observations on these variables. That is, we have data on 1,000 individuals, their decision to purchase a car or not, and their income, age, and gender. Using this data, we will illustrate how to estimate the Logit model, probabilities, and marginal effects including average marginal effects at mean and marginal effects at representative values. Now, let us move on to the estimation of this Logit model. In R, we can use the glm function provided by the stats package. In the command shown here, we will save the results of Logit model in the object named Logit. In the glm function, we will first specify the model equation. X is the dependent variable here and income, age, and gender are the independent variables. It is important to note here that we specified gender as a factor variable, which implies it is a categorical variable. This is essential because the marginal effects will be different if we don't specify it as a factor or categorical variable. The Logit model results will be the same either way, but marginal effects estimated from the model will not be the same. Hence, we must specify the categorical variables correctly. In the family option, we will choose binomial and specify the link function as Logit. This is because we are estimating the Logit model. Finally, we have to mention the dataset we are using, which is the car purchase data in our example. This command will estimate the Logit model and save the results in Logit object. We can see the results using the summary function. In Stata, we can use the Logit function to estimate the Logit model. We can do this using a simple command as shown here. After mentioning Logit, we specify the dependent variable x followed by the independent variables income, age, and gender. Again, it is important to specify gender as a factor or categorical variable. In Stata, we can do this using the i.gender as shown here. Even though the Logit model results will be the same, this is essential because the marginal effects will be different if we don't specify it as a factor variable. This command will estimate and return the results of the Logit model. Both these commands in R and Stata will return the same results and estimates of the Logit model. Let us take a look at the results of the Logit model we estimated. Along with the estimated coefficients, we also get the standard errors, z and p-values. The coefficient of income is 0.040435, age is 0.219499, and gender is 0.318435 as we can see in the results. The interpretation of these coefficients does not make economic sense as we discussed in the previous tutorials. These coefficients show changes in log odds of purchasing a car and not in terms of probability. For instance, the coefficient associated with age is 0.219499. If age increases by 1 year, the log odds of purchasing a car increase by 0.219499. In case of gender, being a male increases these log odds by 0.318435. We can still assess whether the variables are positively or negatively related. In our example, we can see that income and age have a positive effect on the decision to purchase a car. That is, increase in income or age leads to an increase in the probability of purchasing a car. For gender, being a male increases the probability of purchasing a car. However, we need to estimate the marginal effects to gain a deeper understanding of the relationships and the magnitude of change in probability. Using marginal effects, we can analyze the changes in independent variables and their magnitude of effect on the probability of purchasing a car. In the previous tutorial, we discussed that we must choose the values of the independent variables when estimating the marginal effects. There are 3 different approaches that we can take, each gives us a different way of estimating the marginal effects after the Logit model. These are average marginal effects or AMEs, marginal effects at mean or MEMs, and marginal effects at representative values or MERs. We can estimate all these types of marginal effects in R and Stata. First, let us discuss the average marginal effects or AMEs. In AMEs, marginal effects are estimated for all the values of independent variables in the sample, and then their mean or average is calculated to obtain the average marginal effects. In our example, we had 1,000 observations, each with a different set of values for independent variables. As a result, we obtain the marginal effects for all the 1,000 sample observations, and then we take their mean to arrive at the average marginal effects or AMEs. We can use the commands shown here to estimate the average marginal effects in R and Stata. In Stata, we can use the margins command to estimate the average marginal effects. Similarly, the margins package can be used to obtain the same results and average marginal effects in R. Both the commands shown here give the same results for average marginal effects. On average, the probability of purchasing a car increases by 2.63% with a small increase in age of an individual, given that income and gender stay the same. In case of gender, males have a 3.78% higher probability of purchasing a car on average, given the age and income. Similarly, probability of purchasing a car increases by 0.48% on average as income increases by small amount as age and gender stay the same. It is important to note here that these are the average effects. Let us consider the average marginal effects of age. The marginal effects are actually different at different ages, that is, the change in probability is different at different ages. For instance, the marginal effects at age 30 will be different than marginal effects at age 60. The value of AMEs at 2.63% is simply the average of all those marginal effects of age at different ages, incomes, and gender. This is one of the major disadvantages of AMEs or average marginal effects. They reduce the marginal effects to a single value, even though the marginal effects are different at different values of variables. We got an average marginal effect of 2.63% for age, which is single value or number. However, it doesn't allow us to analyze the changes in probability of purchasing a car at different levels of age or income. On the other hand, these commands also provide us with a lot of flexibility. For instance, we have a categorical variable of gender in our example. Suppose we want to estimate the average marginal effects for males and females separately, we can easily do this with the commands shown here. The results including the AMEs for males and females are shown in the table. Let us look at the age variable first. On average, the probability of purchasing a car increases by 2.55% for females and 2.66% for males as age increases by small amount and income stays constant. Similarly, the probability of purchasing a car increases by 0.47% for females and 0.49% for males on average, as income increases by small amount and age stays the same. Now, let us discuss the marginal effects at mean or MEMs. As the name suggests, these marginal effects are calculated at the mean of the variables. One of the drawbacks of this approach is that taking the mean of categorical variables does not make much sense. In our example, gender is a categorical variable that takes the value of either 0 or 1. The mean of this variable will simply show the proportion of males and females in our sample, and it will be a value somewhere between 0 and 1. For example, a mean of 0.6 for gender implies that we calculate the marginal effects at 0.6 value of gender. This does not make sense because how can someone be 0.6% male? It is not a reasonable value to consider. As a result, we will illustrate marginal effects by taking the mean values of age and income only. For gender, we will simply estimate marginal effects separately for males and females. To do this, we can use the commands shown here. In R, we can use the margins function same as before. The Logit object contains the results of our estimated Logit model. The variables option can be used to specify the variables that we want to estimate the marginal effects for. Here, we will choose age and income because we want to see how the probability of purchasing a car is affected by changes in age and income. That option can be used to specify the exact values where we want to estimate the marginal effects. Since we are using mean values, we will take the mean of age and income and specify it within this option. Moreover, we will also specify the gender categories of 0 and 1 to estimate the marginal effects for males and females separately. In Stata, we can use the AMEs option to accomplish this. After margins function, we have specified gender here, which is a categorical variable. By doing this, the command will estimate the marginal effects for males and females separately. If we don't specify this, then the function will calculate marginal effects at the mean of gender, which does not make much sense here. The results of the commands are shown here. As we can see, the mean of income is 60.5742 and the mean of age is 40.1060. Hence, these marginal effects are calculated at these mean values of age and income. As age increases by small amount from 40.1060 keeping income constant at 60.5742, the probability of purchasing a car increases by 4.46% for females and 5.01% for males. Similarly, as income increases by small amount from 60.5742 keeping age constant at 40.1060, the probability of purchasing a car increases by 0.82% for females and 0.92% for males. This approach, however, also has a similar drawback to that of average marginal effects. It reduces the marginal effects to a single value. We have calculated marginal effects at mean values only, even though we know that marginal effects are different at different values or levels of independent variables. Finally, we can estimate the marginal effects at representative values or MERs. The MERs can be used to eliminate the drawback of AMEs and MEMs. That is, we can estimate the marginal effects at different values of independent variables. For example, we can choose values of independent variables that hold some economic importance or choose a set of values to analyze how marginal effects behave at different values. In our example, this would imply choosing a set of different values for age and income. Suppose we want to analyze how the probability of purchasing a car changes at different ages and incomes, then we can use the command shown here to estimate the marginal effects. In that option, we have specified ages of 30 and 60 and income of 30 and 120. Therefore, the functions will estimate the marginal effects at these different levels of age and income. The results of these commands are shown here, and let us interpret some of these results for better understanding. As age increases by small amount from 30, keeping income constant at 30, the probability of purchasing a car increases by 0.31%. As age increases by small amount from 30, keeping income constant at 120, the probability of purchasing a car increases by 5.02%. This change in probability is so much bigger because the income was at 30 earlier and now it is at 120. Now let us look at the marginal effects at age 60 and income 120, which are both high values of income and age. The change in probability is again small at only 0.05%. We can see similar results in case of marginal effects of income. As income increases by small amount from 30, keeping age constant at 30, probability increases by only 0.06%. At 120 income, this marginal effect is much bigger at 0.92%. Then at high levels of both age and income, the marginal effect is again small at only 0.01%. This happens because we are approaching very high or extreme values of income and age. As discussed in previous tutorials, the changes in probability will be small at extreme levels of variables. This also makes economic sense because at low income of 30, the affordability of car is less and so the marginal effect is 0.31% only. At very high income of 120 and age 60, marginal effect is again small at 0.05%. This is most likely due to the advanced age of the individual and the fact that he/she probably has a car already with 120 income and does not need to purchase another. Since gender is a binary categorical variable with 1 equal to male, the marginal effects show the difference in probability of males and females at the chosen ages and incomes. For example, at age 30 and income 30, males have a 0.46% higher probability of purchasing a car. At age 30 and income 120, males have a 7.31% higher probability of purchasing a car, and so on. The advantage of this approach is clearly visible in this example. In case of average marginal effects and marginal effects at mean, we got a single value that did not give us detailed information on the effects of variables. However, we can choose any value or sets of values while estimating marginal effects at representative values. These MERs help us analyze a lot more information about the changes in probability. Thank you for watching, and I will see you in the next tutorial.